Hello, this is Dr. Hanaa Assil, and today we're talking about organic chemistry of Unit 2 in the IAS Edexcel chemistry. So this includes alcohols and halogenoalkanes. If you remember from previous courses, alcohols contain the functional group OH. So we have methanol, ethanol, propanol, butanol, all of them have OHs in them. Now we need to classify the alcohols into primary alcohol, secondary alcohol, and tertiary alcohol. The primary alcohol has the OH on one end of the chain, and that means that the carbon to which the OH is attached to only one carbon. So we say it is primary alcohol. Now the secondary alcohol, the OH is in the middle. And that means the carbon to which the OH is attached is bonded to two carbon atoms. Now, a tertiary alcohol will have the OH attached to a carbon that is bonded to three other carbons. So please note which one is primary, secondary, and tertiary. So this is a question, for example, which of the following is a tertiary alcohol? So you need to draw all of these to be able to determine if it is primary or secondary or tertiary. So for example, how do we draw 3-methyl butane 2-ol? You should remember that butane means I have 4 carbons. The 2-ol means that my OH is on carbon number 2. And the 3-methyl means that the methyl is on carbon number 3. So this is the kind of compound we're looking at. Okay, so 3-methyl butane 2-ol, that is my first one. Is that a tertiary alcohol? Well, let's see. The OH is attached to a carbon that is attached to 2 carbons. So actually, this is a secondary alcohol. Now, 2-methyl butane 2-ol. 2-methyl butane 2-ol. This would be the compound. Now, what kind of alcohol is that? The OH is attached to a carbon that is attached to 3 other carbons. This is a tertiary alcohol. So this would be my answer. Let's take a look at the others. 2-methyl butane 1-ol. This is how you draw it. 2-methyl butane 1-ol. Of course, you should realize that if he says 1-ol anyway, that means that the OH is on the end, so that's actually a primary alcohol. Now he has 2,2-dimethyl propane 1-ol. 2,2-dimethyl propane 1-ol would look like this, and this is also a primary alcohol. So my answer here is B. Okay, this is another typical question. There are 2 alcohol structural isomers with this molecular formula. Give the skeletal. Again, pay attention. Is he asking for skeletal or displayed or structural? So here he wants the skeletal formula. The skeletal formula of the isomers that have 3 carbons. So what we have is an alcohol with 3 carbons. Now, what would be the kind of isomers that we have? Either the OH is on one end, and that means that this is a primary alcohol. And what would be its name? This is propane 1-ol. Now, what would be the isomers of that? The isomer of that is when I put the OH in the middle. So if I put the OH in the middle, now what is it called? It is propane 2-ol, and that is a secondary alcohol. Okay? Which is the order of increasing boiling temperatures? Do you remember the boiling temperatures depend on what? First of all, they depend on number of carbons. So we said if the number of carbons increase, the boiling point increases. But here all my choices have 4 carbons. So that would not affect my boiling temperatures. Okay. What is the difference between these 4 structures? Well, the difference is the number of OHs. Remember that each OH in a compound can do a hydrogen bond. The more the OHs, the more the hydrogen bonds. That means the stronger intermolecular forces, and that means the higher boiling temperature. So if we're putting them in order of increasing, that means I'm starting with the lowest and then the higher and higher and higher. So which of these would have the lowest temperature, boiling temperature? Well, actually that would be Y, because Y is just an alkane. It doesn't have OHs, so the only intermolecular forces between its molecules would be weak London dispersion forces or van der Waals forces, so that would have the lowest boiling temperatures. Now all the others have OHs. The more the OH, the more the hydrogen bonding per molecule and the higher the boiling temperature. So that means X has one OH, Z has two OHs, W has three OHs, so that would be the highest boiling temperature. Okay, you remember that ethanol is a typical alcohol. We use ethanol for fuel or solvent or to make beer or perfumes, and the reactions of alcohols. Okay, basically the first reaction is combustion. We said for all alkenes or alcohols, all of them do combustion. Combustion means burning or reaction with oxygen, and we said if we have excess oxygen, that is complete combustion, and that gives carbon dioxide plus water. If we have limited amount of oxygen or lack of oxygen, that is incomplete combustion, and that will give us only carbon monoxide plus water. So this is a question. Alcohols can undergo complete or incomplete combustion. Write the equation for the complete combustion of this compound. And we said complete combustion means they react with oxygen to give carbon dioxide plus water. And please do not forget to balance the equation. And then he says, write the equation for the incomplete combustion. The incomplete combustion, he's telling me that it will produce carbon and water. Remember that incomplete combustion, we said, it can give carbon monoxide and water. It can give only carbon and water, and actually it can give a mixture of all three, carbon monoxide and carbon and water. So here he's telling me it will give carbon and water, so I balance the equation based on that. Okay, another reaction of alcohols is the reaction with a metal. Like sodium, we said that the alcohol, if it reacts with a metal, we remove the H of the OH and we place the metal instead of it, and the naming of the compound would be sodium ethoxide. And the other product, of course, is hydrogen gas. This is a metal with an alcohol. It gives the sodium salt plus hydrogen gas. Now, this question says, how would you test for the OH group in 2-methyl-propane-tol without using phosphorus pentachloride? We're going to be talking about phosphorus pentachloride in a minute, but if he says you're testing it without the PCl5, then you would test it with sodium. Remember that if you add sodium to an alcohol, it gives hydrogen gas, and that means you should see bubbles of gas. Now, another test for alcohols is its reaction with phosphorus pentachloride, which is PCl5. If we put PCl5 on alcohol, it reacts and it gives HCl, which appears in the form of white fumes. The only problem with that is we will get white fumes if we add PCl5 to alcohols and to acids. So it cannot be used to distinguish between alcohols and acids. But if he says what is the test for alcohols, you could say add PCl5, it gives white fumes of HCl. So this is a question. He says write the equation for the reaction between methanol and phosphorus chloride. Did you notice what you get when you add alcohol to PCl5? It will give you the chloride, the methyl chloride or chloromethane, plus POCl3 plus HCl. And then if you need to balance, it should be balanced. The observation for this, we said if it gives off HCl, it gives what we call steamy white fumes. These reactions you need to know. So another reaction of alcohol is if I want to replace the OH with a Br. So I want to prepare a bromoalkane from an alcohol. I add potassium bromide and 50% concentrated sulfuric acid. This will replace the OH with a Br, and the other product is water. Another reaction is if I want to replace the OH with iodine. Then I react the alcohol with iodine in presence of red phosphorus. That will replace the OH with iodine. Another reaction is the dehydration of alcohols to form alkenes. So if I want to remove the OH and change the alcohol into an alkene, I can heat it with concentrated phosphoric acid. So that will remove H and OH, so it removes water and forms a double bond between the two carbons. The other reaction is oxidation of alcohols. Now, remember, first of all, if I have an alcohol and I need to oxidize it, the oxidizing agent could be potassium dichromate, which is K2Cr2O7, in presence of sulfuric acid, or potassium manganate, KMnO4, in presence of sulfuric acid. These were the two oxidizing agents that we talked about in O level. So if I want to oxidize an alcohol, I need you to remember that oxidizing primary alcohols is different from secondary, is different from tertiary. Now, if we're trying to oxidize a primary alcohol, remember we said primary alcohol means the OH is on one end of the molecule. Now, the first thing that will be produced is called an aldehyde. Can you see the functional group of the aldehyde? Aldehydes have C double bond OH. That is an aldehyde. Now, if I continue to heat with potassium dichromate, I will eventually end up with the corresponding acid. So primary alcohols give aldehydes first, and then if you continue to heat it with the oxidizing agent, it will give acid. That means that I need two different techniques if I want to obtain aldehyde or if I want to obtain acid. So if I have an alcohol and I'm trying to obtain aldehyde, then we can heat the alcohol with the oxidizing agent in a flask, and as soon as the aldehyde comes out, I can distill it off through a condenser and collect it as soon as it is formed. In this case, the primary alcohol will be oxidized to form an aldehyde. But if I want to obtain an acid, that means I need to heat it for longer time. But the problem is alcohols are volatile, so I cannot really heat them without evaporating the alcohol. So I need to do what we call heating under reflux. That means I place the condenser, as you see, and I heat the solution. If any of the alcohol evaporates, it will be cooled down in the condenser and it will condense back and return back into the flask so that I can heat the alcohol for a long time and eventually end up with the acid. So if we want to make sure if we have aldehydes or acids in our solution, there is a test for aldehydes. To test for the presence of aldehydes, we add what we call Benedict solution or Fehling solution. If the aldehyde is present, it will form a brick red precipitate, and that would indicate that I have an aldehyde. To test for acids, you should know that to test for acids, we add a carbonate like sodium carbonate or sodium hydrogen carbonate. And if we have an acid, there will be bubbles of gas that turn lime water milky. Or we could also add sodium, and sodium causes effervescence or bubbles of hydrogen gas. Now, what if we are oxidizing a secondary alcohol? Now, to oxidize the secondary alcohol, if we add potassium dichromate and dilute sulfuric acid to something that has a secondary alcohol, it will change into what we call a ketone. Can you see the functional group of ketones? Ketones have only C double bond O in the middle of the molecule. That's a ketone. If we try to oxidize a tertiary alcohol, it doesn't work at all. There is no reaction. So a tertiary alcohol cannot be oxidized. So let's look at this question. Which of these compounds would not produce a color change when heated with sodium dichromate? I want you to remember that dichromate solutions, potassium dichromate or sodium dichromate, are originally orange in color, and when they react, they change to green. So, which of these would not produce the color change? That means which of these I cannot oxidize, which of these will not react with the oxidizing agent. And we said the only one that will not react with an oxidizing agent is either an acid or a ketone, because the ketone is the final product, we cannot get it. But aldehydes can be oxidized, alcohols can be oxidized. So, which of these would not produce a color change? Well, let's take a look. Butane 1-ol is a primary alcohol. It would be oxidized to give the aldehyde or the acid, depending on how long you heat it with the oxidizing agent. Butane 2-ol is a secondary alcohol, and we said if we try to oxidize a secondary alcohol, it will give a ketone. Now, C butanal. Butanal is an aldehyde. Remember that if we oxidize the aldehyde, it becomes acid. Remember when we were saying primary alcohols give aldehydes, and then further oxidation will change the aldehyde into acids. But butanone, that is a ketone. Remember that ketones cannot be further oxidized. So the ones that cannot be oxidized are tertiary alcohols, acids, and ketones. Okay, which of the following compounds could be oxidized to a carboxylic acid by refluxing with potassium dichromate? Remember, the one that gives me carboxylic acid is the primary alcohol. The secondary would give ketone. The tertiary would not react at all. So the question is, which of these is a primary alcohol? So of course, if you look at D, D is a primary alcohol. A is a secondary. B is a tertiary alcohol. C again is a secondary. D is the only one that is a primary alcohol, and we said if you oxidize primary alcohols, they will eventually give acids. Ethanol can be oxidized to ethanoic acid. Give the formula of a suitable oxidizing agent. Remember, oxidizing agent can be potassium dichromate in presence of sulfuric acid. Now, using the symbol of oxygen for the oxidizing agent, write the equation for oxidation of ethanol to ethanoic acid. So we write it just with an O to represent the oxidizing agent. Remember that we have, in order to balance this, the ethanol becomes ethanoic acid, and we have the other product is water. Draw and fully label the apparatus that would be used to carry out complete oxidation of ethanol to ethanoic acid. Remember, if I want the primary alcohol to continue oxidations until it forms acid, I need to heat it under reflux. And we said this is the kind of apparatus that we use for heating under reflux. He says include any material that would be used to ensure that boiling is controlled. Can you see the anti-bumping granules? When we're trying to heat these reactions and we don't want it to bump or to be very violent or to jump out or things like that, we add anti-bumping granules, which are actually tiny little, in most cases, they're just tiny little glass beads. The presence of these in the solution prevents it from bumping or from boiling violently. This other question says ethanol can be oxidized to an aldehyde using the apparatus shown. Remember we said if we want to stop in the middle at aldehydes, then I have to distill the product as soon as it is formed. State the class of alcohols that can be oxidized to aldehydes. We said the ones that can be oxidized to aldehydes are the primary alcohols. Okay, halogenoalkanes. Halogenoalkanes are basically alkanes that have halogens. So we still can classify them as primary, secondary, and tertiary. So if the Br is attached to a carbon that is attached to only one carbon, that's primary. If the Br is attached to a carbon that is bonded to two carbons, that's secondary. If the Br is attached to a carbon that is bonded to three carbons, that's a tertiary halogenoalkane. So if we look at halogens, halogens are more electronegative than carbons, so they will form dipoles. So usually you will have a slightly positive, slightly negative between the carbon and the halogens. Now you should remember that the halogens at the top of the group are more electronegative, so there will be stronger dipole-dipole interactions. Electronegativity decreases going down the group, so the bond polarity would decrease. The bond strength, as we go down, we say that the fluorines or the halogens are getting bigger. We said before that this means that the bonds between the carbon and the halogen will be weaker since the halogens are becoming bigger and there is less attraction between the bonding pairs of electrons and the positive nucleus of the halogens, so they will be more easily broken as we go down the group. How do we make halogenoalkanes? We already said if I want to change OH to Br, then I can put potassium bromide and 50% concentrated sulfuric acid. So this question, for example, says 2-methyl-propane-1-ol has the skeletal formula of this. 2-methyl-propane-1-ol can be converted to 1-bromo-2-methyl. So he's trying to remove the OH and put Br. We said what are the reagents and conditions? The reagent is KBr and 50% sulfuric acid, and the condition is heat under reflux. That's what we should do. Okay, now nucleophilic substitution reactions. We said substitution reactions means something attacks and replaces what is in the molecule. Nucleophilic means we are attacking or we are reacting with something that has extra electrons or something that has a negative charge. So ammonia, for example, has the nitrogen has a lone pair of electrons. It will attack the carbon that has the Br and replace the Br. So if I want to remove the Br and put NH2 instead of it, and remember the compound that contains NH2 is called an amine, then I need to react the halogenoalkane with ammonia in presence of ethanol and heat in a sealed tube. These are the conditions. Remember to prepare an amine. An amine is something that has NH2. You need to replace the Br with NH2. That means you react the halogenoalkane with ammonia in presence of ethanol and heat in a sealed tube. What if I have the halogenoalkane, I want to go back to the alcohol? Then I react it with potassium hydroxide in water and heat. And remember, this is potassium hydroxide in water and heat. It's very important that this is aqueous potassium hydroxide. Now, if I want to replace the Br with OH also, I can also say react with aqueous silver nitrate and ethanol. That would also change the halogenoalkane into an alcohol. Now, if I want to replace the Br with CN, CN is a nitrile group, we react the halogenoalkane with alcoholic KCN. So that means it is potassium cyanide in presence of ethanol. The mechanism of nucleophilic substitution reactions you should be familiar with. We said nucleophilic means I'm reacting with a nucleophile. We said a nucleophile is something that has extra lone pair of electrons or it has a negative charge. These lone pair of electrons will attack the slightly positive carbon atom. Remember that we said the CBr bond has dipoles. So the carbon is slightly positive, the Br is slightly negative. So the nucleophile attacks the slightly positive carbon and pushes out the bromine, so it replaces the Br with the cyanide group. Now, what is the reactivity of halogenoalkanes? Remember that we said the Ci bond is weaker than the CBr bond, and the CBr bond will break more easily than the CCl bond, and that means the iodo compound is more likely to react faster than the bromo, faster than the chloro. Now, if we're talking about which type of alcohol we're trying to replace, remember that in nucleophilic reactions, the order of reactivity is the tertiary alcohol will react faster than the secondary, faster than the primary. So a question like this, which compound is hydrolyzed most rapidly? So we want to know which of these would react faster. Remember that 1-chloropropane, that's a CCl bond. 1-chlorobutane is also a primary halogenoalkane. Now 2-chloro, 2-methyl, this is what kind of halogenoalkane? This is a tertiary halogenoalkane, and we said that the tertiary is more likely to react faster than the secondary, faster than the primary. Alcohols can be produced from the reaction of halogenoalkanes with aqueous alkali. Draw the mechanism for this reaction with 1-bromopropane. Show the lone pair involved in the mechanism and any relevant dipoles and curly arrows. So remember that this is how you should draw the mechanism. You have, he's saying, start with 1-bromopropane. The OH hydroxide group has a lone pair of electrons, so the electrons will attack the slightly positive carbon, and the bonding pairs of electrons will go to the Br, so you end up with the alcohol plus Br minus with a full negative charge, not a slightly negative charge. This other question says 1-bromobutane reacts with alkali. The mechanism and type of reaction is what? We said if I'm trying to replace the Br with OH, I'm reacting with the OH minus. First of all, is it electrophilic or nucleophilic? We said we're reacting with OH minus. This is a nucleophile. So this is nucleophilic. Now it's nucleophilic what? We call it nucleophilic substitution because we're replacing the Br with an OH. This question says 1-bromo 2-methyl propane can be converted back to 2-methyl propane 1-ol by heating with aqueous alkali. So he's heating this halogenoalkane with an alkali. Identify and correct the 3 mistakes in this mechanism. Can you see any mistakes in these mechanisms? Well, there are 3 mistakes. First of all, the dipoles are wrong. He has a slightly negative on the carbon and a slightly positive on the Br. That's wrong. And he has the arrow going from the carbon to the OH minus. That is wrong. So dipoles on the CBr are reversed. That's wrong. The arrow from the OH minus to C is reversed. It should go from OH minus to the C. And the OH minus should have a lone pair of electrons on the oxygen. Okay, so this is a wrong mechanism that he drew. Now, treatment of 2-bromoethanol with aqueous sodium hydroxide would be one way to produce ethane 1,2-diol. Complete a possible mechanism. So he has the halogenoalkane and he's trying to react it with a hydroxide ion. So of course we said the electrons on the OH minus will attack the carbon that is slightly positive, and the bonding pairs of electrons will go to the Br, so that my other product is Br minus. Classify the mechanism. The mechanism we said is nucleophilic, and the type is a substitution reaction. Okay, another reaction is elimination, or what we call dehydrohalogenation. So if I put potassium hydroxide in ethanol, alcoholic KOH, remember, there was another reaction where we did potassium hydroxide in water, aqueous KOH, just replace the Br with OH. But if it is alcoholic KOH or KOH in ethanol and heat, it removes H and Br, so it forms alkene. This is an elimination reaction, or what we call dehydrohalogenation. The mechanism of this, please note, it is still nucleophilic because the OH minus is a nucleophile that is attacking, but this is nucleophilic elimination. So notice that the OH minus is not attacking the carbon. It is attacking the hydrogen on the nearby carbon. So it's attacking the hydrogen. Now the bonding pairs of electrons will go between the two carbons, and the bonding pair of electrons between the C and Br will go to the Br. So of course the other product here would be Br minus. The reaction of 1-bromopropane with concentrated alcoholic alkali forms a different organic product. Name the type of reaction. So when we have a bromopropane with alcoholic alkali, we said this is called elimination, and what we have is the alkene, not substitution of the Br with OH. Here he's saying 1-bromo-2-methyl propane can be converted to 2-methyl propene. Again, what would be the reagents? The reagent is KOH. The conditions are it has to be in ethanol and heat under reflux. That's the one that will give the alkene. So this is a summary of all the reactions that you need for organic. We said addition reactions of alkenes. If you're adding hydrogen, it has to be in presence of nickel catalyst and 180 degrees centigrade. It gives the alkane. If I'm reacting with bromine, it will give the dibromo product, 1,2-dibromo. These are addition reactions. Now, elimination is where I change the alcohol into alkene, and we said conditions here could be concentrate sulfuric acid 180 degrees Celsius or aluminum oxide catalyst and heat, that is elimination reaction. Nucleophilic substitution is where we attack with a nucleophile to replace the OH. So sodium bromide, for example, would replace the alcohol with a Br. Oxidation, we said if we're oxidizing primary alcohols, it will change into an aldehyde first and then an acid. Reduction, if we're adding with hydrogen, this was called addition reaction, but it is also a type of reduction because this is gain of hydrogen. Hydrolysis means breakup of compound using heat and usually acid, dilute acid. So, for example, if I heat an ester with water in presence of concentrated sulfuric acid, it will break up the ester into the original acid and alcohol. Polymerization, you should remember from O-level, if we have an alkene, it polymerizes to form a long chain of polyethene, for example. Okay, thank you for listening, and please continue studying.